All right, standard enthalpies of formation are values that we can look up. Every molecule has a fixed amount of energy associated with the formation of that molecule. This first part here says, using the appendix, look up the standard enthalpies of formation for these substances. It's on page A19 of your book. It's in the very back because that's an appendix. Aluminum oxide is going to be negative 1,676 kilojoules per mole. Titanium is in its standard state, so that's going to be 0. So anything in its standard state, well, you don't really require energy to make it because it's already there, so it's a value of 0. P4, interestingly enough, if you look at that one, there are a couple different kinds of phosphorus. P4 happens to not be the standard one, so 59 is the value there, kilojoules per mole. Sulfate is negative 909 kilojoules per mole, and then diatomic gaseous fluorine is 0. You need to be careful for these that they need to be in the right phase, diatomic versus monoatomic, to be their standard states. So watch out for those. There are a couple liquids. Bromine and mercury are liquids, so pay attention. And just a reminder, let me do A for a minute, that these are, we can write a balanced equation that goes with any of these. So when we talk about enthalpies, this is 2 aluminums, solid, plus, this is where we're going to get fractions, 3 half oxygens, gas, makes 1 Al2O3, solid. So that negative 1676 is the heat of formation for this equation. Now, why do we call it a heat of formation for this, and why do we have fractions? Because a heat of formation requires these to be elements in their standard state, which means diatomic, monoatomic, solid, liquid, or gas, and it requires us to have 1 mole of product, just 1 single mole. So this is the only instance where we really get fractions in our balanced equations. So the heat of formation definition is going to guide those balanced equations. And the thought behind this is going to be, so why does that value go with just the products? Well, if these are elements in their standard state, this has a heat of formation of 0, the oxygen has 0. And if both of the elements are 0, then anything associated with the product is exclusively associated with the product. So we can say that, yes, this equation is negative 1676, but it is also going to be associated with that one molecule, which is why we can call it just the energy of that molecule. All right. And then if we have all of those molecules listed, we can use the formation for each one to get for a balanced equation, an actual reaction. This is the summation equation. We look all of these up, and we have 20.9 is that heat of formation. Oxygen is going to be 0. Carbon dioxide is negative 393.5. And the water is negative 286. So now the coefficients are going to come into play, and we need to remember products minus reactants. Products minus reactants. If we're really careful here, we know we're going to have 6 carbon dioxides. Don't take shortcuts with this. It's worth writing all of these down. 6 waters, and you always need to watch out, solid, liquid, or gas, especially with the water. Those are my products, minus the reactants. 2 C3H6s plus 9 O2s. Okay, so we start plugging those in, and we get 6. Carbon dioxide is negative 393.5. 6 waters is going to be negative 286. 2 times 20.9. Make sure you get that negative sign. It's going to distribute everywhere. I know that oxygen in this case is 0, so it's going to go away, but you need to make sure you just watch out for the signs. If you make any mistakes in here at all, it's going to be just the signs. So don't miss silly points here just because you're not writing careful numbers down. This is going to be negative 4,119 kilojoules. The moles go away because the coefficients do represent the moles. So for this equation, this is now, we will call this a heat of combustion. You might see that. That goes to the whole equation, all of those things. Or we might just generically, we can say for any of these, it's the heat of the reaction. So we'll see different subscripts on those. Here's another one then. Calculate the heat for this reaction. So we get our aluminum and our chromium are in standard state. The chromium 3 oxide is negative 1128 kilojoules. And the aluminum oxide is negative 1676. Okay. If we get our formation equation, since the chromium is 0 and the aluminum is 0, my product is the aluminum oxide, negative 1676, minus my reactant, which is negative 1128. So both the coefficients are 1 there. The heat of the reaction is going to be negative 548 kilojoules. Okay, now we can use this as a conversion. We've seen it before, but now you're calculating it and then using it as a conversion. How much energy is made per gram of chromium? So now we want to isolate the chromium, and we say this much energy goes with 2 chromiums. So when we set this up, we say, okay, I have negative 548 kilojoules of energy released for every 2 moles of chromium, because the coefficients go with that. If I need this per grams, all I need to do is cancel out the moles. This is kilojoules per mole. I need kilojoules per gram. So if I have moles of chromium into grams of chromium, moles will cancel out, and now I have kilojoules per gram. To do that, we just need the molar mass. 1 mole of chromium is 52.00 grams. And that's going to give me negative 5.27 kilojoules per gram. And we have to specify here, this is for chromium. It would not be the same kilojoules per gram of aluminum or aluminum oxide. This is just the chromium. So we just got to be careful to our units, our coefficients, and some molar masses, and we can convert any of these energies into moles and grams and use them with stoichiometry as well.